Hello everyone! Today we will continue to look at the content of HCI-Storage. Previously, we have already introduced two different expansion methods. Next, we will take Huawei's SS hard disk enclosure as an example to explain in detail our method of scale-up expansion. The expansion principles. First of all, scale up. In terms of networking, simply put, it is a vertical expansion method for our storage system. Well, using a warehouse as an analogy, it is actually like this. If your warehouse is running out of space, how do we increase it? By adding more shelves, right? This is essentially like adding more hard drive enclosures to accommodate these goods. Rather than building a new warehouse, this is the basic idea behind the scale-up networking approach. In the initial stages of expansion, this method is actually quite good, right? For a warehouse, at the beginning, it's unlikely that the entire warehouse would be filled with shelves. If it's not enough, we can simply add new shelves within the warehouse. This is the first method, a way of vertical expansion. Now let's take a look at the main network diagram, of Huawei's SAS hard disk frame in our PPT. From the figure, we can clearly see that we have a control frame. Here. Above, this is the control enclosure. It acts like the commander of our entire storage system, responsible for managing and scheduling data below the control enclosure. There are two USS disk enclosures here, which we can respectively call Yemanguang 0 and Yemanguang 1. These disk enclosures are places for actual data storage, much like storage shelves in a warehouse. Next, let's discuss in detail the specific principles of our network setup. First, the primary principle is the port correspondence principle. Within the same loop, the downstream port of the upper-level disk enclosure should connect to the upstream port of the next level disk enclosure. It means they need to be connected front and back. Front and back. For example, you can take a look at this part here. It's from this position. It's like saying our upper level. Especially here where we have two disk enclosures. Let's compare these two disk enclosures. Here is the downstream port of our upper level disk enclosure. Connect to the upstream port of our next level disk enclosure. Although this one above is not considered a disk enclosure, the principle is the same when connecting. The downstream port above connects to the upstream port below. In this way, it actually facilitates data transmission and data relay. This is equivalent to the upper level disk enclosure transmitting data through the downstream port to the upstream port of the next level. If the ports are connected incorrectly, then data transmission will encounter problems. It's like, well, a relay baton in a race. Under normal circumstances, our upper level disk enclosure passes the relay baton from its downstream port to the upstream port of the next level disk enclosure. If your downstream port is connected to its downstream port, and then your remaining upstream port is connected to its upstream port, then everything becomes completely mixed up. In this case, everything becomes completely mixed up, and data transmission will encounter problems. So here, everyone must pay attention. If we assume that disk enclosure 0 is the upper level, and disk enclosure 1 is the next level, then the downstream port of 0 must be connected to the upstream port of 1. This ensures that our data flows orderly between the disk enclosures. This is our first principle, which is the port correspondence principle. This port correspondence does not mean connecting the upstream port to the upstream port and the downstream port to the downstream port. That's incorrect. It must be that the downstream port of the previous disk enclosure is connected to the upstream port of the next one. That's it. It's like they are connected end to end. You can think of it as end to end. Hey, it's like the tail of our previous hard drive is connected to the head of the next hard drive, right? This is the back end, and this is the front end, so that we can connect them normally. Including this part below. What do we actually have here? Because here we have a 2U hard drive enclosure, so we have two lines here. For 2U, there are two lines. For 1U, there is one line. For 2U, there are two lines. You see the second line. The blue line here is the same. It means connecting the lower heart to the upper heart. The same meaning. So this is our port correspondence principle. This is the first principle. The second principle is the dual plane networking principle. What is dual plane? That is the A level. The A cascade board connects to the A controller, and the B cascade board connects to the B controller. Here you can imagine the controllers as two different managers. The A cascade board and the B cascade board are like their respective assistants. Each assistant needs to closely cooperate with the corresponding manager, right? This way we can better manage our disk enclosures, if you connect them incorrectly. It's like you've registered with the wrong manager. In this case, the work might become somewhat chaotic. In an actual storage system, if your A node board is incorrectly connected to the B controller, what would this lead to? This would lead to chaos in data transmission and management, including serious issues like data loss. The principle of dual plane networking is that they must correspond, meaning the A-level cascade board connects to the A controller, and the B-level cascade board connects to the B controller. This is the second principle, the dual plane networking principle. The next third principle is our symmetrical networking principle. So how do we achieve symmetry? First of all, we have AB. The A and B controllers in the same slots and same port should connect to the same enclosure. These requirements mean that when networking, the A controller and B controller in the same slots and same port should connect to the same disk enclosure. Why is this necessary? It's because this is actually a kind of symmetrical beauty. This is a kind of symmetrical beauty, which ensures that our data is transmitted more evenly and stably between the two controllers. It's like if you are using two hands to carry something. If your two hands exert force unevenly, your items might fall, right? Or it might be more strenuous to carry. In a storage system, if the way controller A connects to the disk enclosure is asymmetrical, it could lead to an unbalanced data transmission load. Some controllers might become overly busy, right? While others might be relatively idle, which would affect the overall performance of our storage system. This is an issue related to our principle of symmetry. Something everyone should pay attention to. We must ensure what must be done with the controllers? They must be symmetrical, absolutely symmetrical. The fourth principle is the positive and negative connection networking principle. What is meant by positive and negative connection? Generally, we connect the positive terminal of the A junction board. For the B junction board, we usually connect it in reverse. However, some storage systems can be entirely positive, which depends on the specific type of storage. It depends on the model of the storage. For example, like the Doradov 6 version, this version is actually the Fusion Storage X10, which is entirely positive. However, in most other cases, we generally connect the A junction board positively, and the B junction board in reverse. This is shocking here. The reverse connection is like the direction in which we plug a plug into a socket. If you plug it in the wrong way, our electrical appliances might not work properly, right? In the storage system, if our junction board is connected incorrectly, it can also lead to issues, such as data not being transmitted, or transmission being inefficient. For example, system failure. For instance, in a conventional network setup, if you connect the B-level I panel correctly, it might cause some errors during data transmission. Impact the normal operation of the storage system. The last principle is our cascading depth principle, which means that the number of cascading control boxes must not exceed the system's maximum cascading depth. This is because as the number of cascading hard drive enclosures increases, the distance and complexity of data transmission will also increase accordingly, much like a water flow in a pipeline, right? The longer the pipeline, the greater the resistance the water flow will encounter. In a storage system, if there are too many cascading hard drive enclosures, exceeding the system's maximum node depth capacity, it may lead to increased data transmission delays and reduced stability. Therefore, we must strictly adhere to these principles to ensure the stable and efficient operation of our storage system. This is us. This is a detailed explanation of the scale-up networking principles for Huawei SAS hard drive enclosures. I believe everyone now has a deeper understanding of this networking method, and in the actual process of storage setup and expansion, it is crucial to strictly adhere to these principles to build a stable and efficient storage environment. That concludes the content of this lesson. If anyone wants to learn Huawei's technology or obtain Huawei certification question banks, please send me a private message. You can also leave comments below the video for technical exchanges. That's it for today. Goodbye, everyone.